All right, Riemann sums. Sounds fancy. Literally all we're going to do today is add areas of rectangles. And I hope your reaction is, like, wait, what else though? Like, that's really it? And I'd say, well, okay, it's not just rectangles, it's also trapezoids. So maybe we need to remind ourselves about trapezoid area. But rectangle area, you should want to be called for rectangle area, right? Say, what's the area of a rectangle? What'd you say? Length times width. Some people say base times height. Like whatever the two dimensions are, that's the area of a rectangle. Easy enough. We're going to add those up today. We're going to do lots of rectangles and then add them up. And it does seem a little bit weird, like how does this guy get credit for adding rectangles? Like what? Feels like that's not a great discovery there. Trapezoids, you remember the formula for a trapezoid though? I'm not going to pull a popsicle stick for that one because
I forgot how to write it, but it's like both of the triangles areas plus the middle rectangle.
Okay. Yes, that would work. We're always going to have like a flat end on one end. So if you do it like that, it would be one triangle plus the rectangle. Emma, does that make sense? And that's not wrong, and that would work. There's a little bit easier way to kind of formalize that or say that. We can just do the average height times the base. So it's sort of like a rectangle, right? But instead of one height, there's two heights. Let's just do the average height times the base. So h1 plus h2 over 2 times the base. So, in my mind, rectangles are base times height. Trapezoids are base times average height. That way they're related to each other. Okay, now let's see if we can figure out how that simple geometry stuff relates to calculus. The motivation here is we want to find the area under a curve from A to B. So you look at those four pictures down below, we're going to be looking for the area underneath that curve down to the x-axis. That's going to be the what we're aiming for. Riemann sum approximations use rectangles to approximate the area under this curve. We use rectangles because we know how to find the area of a rectangle very easily. Riemann sums are named after the German mathematician Bernhard Riemann. Look at that. Guy only lived to be 40 years old. We can draw rectangles using the left side of each rectangle as the height of the rectangle, as opposed to, so let's look at like both of these in tandem before we start drawing pictures. We can also draw rectangles using the right side of each rectangle as the height. And we give them easy names to remember because a left Riemann sum uses the left-hand height. The right Riemann sum uses the right-hand height. So let's use 4 rectangles on each of these. And the fancy word for that we'll start using is subintervals. Right, our interval is A to B. That's the interval we're looking at. But we're going to divide it up into 4 subintervals, aka just 4 rectangles. So probably the easiest way is to cut it in half. So whatever the midpoint is between A and B, and then cut that in half. And that gets us not 4 equal areas, but 4 equal bases. 4 equal bases. And let's do the same thing for the right-hand rectangles. So right now those pictures should look pretty much the same. Okay, left hand Riemann sum, left side, sometimes you hear it called the left-hand sum, but the key word there is left. Left sum, left-hand sum, left Riemann sum. That means we want to make a rectangle, 4 rectangles, and we want to use the left-hand height. So there's one of my rectangles, because I use the left-hand height. Give them the left-hand side of that. My next height, or my next rectangle would be right there. Ooh, I didn't mean to do that all in pink. Yeah, I heard the door too, so maybe they're just checking to make sure it's locked. Left-hand height. Oh, now I messed that up because I used the wrong. Left-hand height. Oh, we should fill these in, I guess. And left-hand height. So 4 rectangles. And we would use the left-hand height each time. As opposed to the second picture, we want to use the right-hand height, the right side. So if I look at my first rectangle, I'm going to use that height, the right-hand height, to make a rectangle. And that rectangle is bigger than the curve, but that's okay. My next rectangle, I would use this height. And the next one would be this height. And that last one would be all of that height. Making rectangles either with the left-hand heights or with the right-hand heights. Question on that? See how to use that in a minute. All right. Those are the 2 most common ones, either from the left or from the right. A little less common, but you still need to know them. We could draw rectangles using the midpoint of each delta x. So let's put 4 subintervals on there again. So of that first interval, the midpoint height means halfway between the 2 left and rights. That would be like midpoint number 1. We would use this height. This is the height at the midpoint. So not the left height, not the right height, but the middle height. There would be midpoint number 2. So we would use this height. Keep it consistent. There's the heights we're using. They're coming from the middle, not the left, not the right, but the middle height. Third midpoint lands right there. Middle height. And then the last midpoint, about right there. So my 4 middle heights. So you can use the left-hand height, the right-hand height, or the middle height. Do you know which one of those would be more accurate? Which one would get us closest to the area? That's kind of a trick question. It depends on the graph. So sometimes the right-hand height would be better, sometimes the left-hand height would be better, sometimes the midpoint would be better. It just depends. What would definitely be better is if we drew trapezoids. So let's do 4 subintervals again on the trapezoid graph. So halfway in between, and then halfway in between. Trapezoids are going to look better. They're going to get closer to the graph because there's my first trapezoid. So there's an H1 and an H2. We'd have to use both of those H's. Then my second trapezoid, they're almost hard to draw because they follow the curve so closely. The second trapezoid. Third trapezoid, not so, maybe not as accurate as the first two there. Looks almost like a rectangle. Might even be a rectangle. And then the last trapezoid. To be a slight overestimate. So trapezoids in general work better than left, right, or midpoint. But do you know what would make it more accurate regardless of whether we were doing left, right, midpoint, or trapezoid? What can we do to make our area estimate more accurate? How many rectangles would, what about the number of rectangles? What's that? Yeah, if you put 8 rectangles in there, it'd be more accurate. If you put 100 rectangles in there, it'd be really accurate. If you put like 1,000 rectangles in there, it'd be a pain to like calculate by hand, but it would be super accurate. And so the more rectangles we add, the better our answer gets, regardless of which method we use. Okay, down here at the bottom, just a reminder, the area is base times height for a rectangle. I'm going to write base and height because that way when I write area of a trapezoid, I can use base and height again, but it's going to be the average height. So for rectangles, you use the height. For trapezoids, you use the average height. That way those formulas look similar enough to help you keep them straight. So use the left, use the right, use the middle, or draw a trapezoid. Do you have a rectangle is base times height? Yes. Each height, okay, here's where we start getting a little more algebra. Each height is the function value at each x value. Another way to say that is each height is the y value at each x value. And each base is delta x. That would be the width of the subinterval. The width of the subinterval. The area is the sum of all the areas. Okay, that looks fancy. There's fancy jargon in here, and here's more fancy symbols coming up. But don't lose sight of the fact that what we're doing today is sum of all the areas of the rectangles. Like, that's all we're doing. So when you go home today and mom or dad ask what you do in calculus, I'm sure they ask that every day, you can say, all we did was add rectangles. And they're going to be like, wait, that's all you did? Yep, that's all we did today was add up rectangles. That's all we're doing. So we're going to put fancy symbols on it. We're talking function values and subintervals, and we can make it sound fancy, but you're just adding up rectangles. You remember what that symbol means? Sum. Again, fancy symbol. Sum the area of each rectangle. So the sum of each height times each base. Sum of each f of x, or each y value, times delta x. Again, this is looking very fancy now, but we're still just adding up areas of rectangles. So, yes, fancy jargon, fancy notation, but don't be fooled. We're just adding rectangles. As you guys mentioned earlier, if we let the number of rectangles go to infinity, now we're thinking calculus. That's not geometry or algebra. That's calculus when we're going to infinity. We get Leibniz's notation for integrals. Again, you're not going to need to know like history of math, who came up with what's the name of the notation. Like that's just kind of thrown in there. You don't have to know that. The summation, that big capital E looking thing, or capital S, is a better way to say that, because it's a sigma for S. If we stretch out an S for sum, we stretch it out and stretch it out and stretch it out, that's really where that came from. That's really what that symbol is. It's a stretched out S, and so it means sum. And if we have delta x, so we're adding up a bunch of f of x's times delta x's, but if we do 1,000,000 rectangles, or 100,000,000 rectangles, or a gazillion rectangles, then it stops going from a delta x to a really, really, really small dx. The official word for that is a differential. So not a delta, but a differential. Infinitely small width. The boundaries on the integral are the x values of the boundaries. The boundaries on the integrals, that would be the boundaries of the integral. Those are the things that go right there and right there, are the x values of the integral. So we're going from a to b. So from a to b. Okay, well, that looks similar to what we've been doing, right? That was the antiderivative, but now I'm telling you it's the sum of the areas. Actually, it's the sum of an infinite number of areas. So that's not an approximation anymore. That's an actual area. Because this means infinite rectangles. We're not going to do infinite rectangles. That would take too long. We're going to do some finite number of rectangles or trapezoids. Heavy in the symbols here. This symbol, it does mean antiderivative, but it also means area. And that'll be a tricky thing moving forward from this day on, is keeping both of those things in mind. When you see that symbol, sometimes it means area, sometimes it means antiderivative. Sometimes it means both. Depends on the problem as to which one matters. That tells you the exact area. We are going to approximate it with rectangles or trapezoids. Either left sum, right sum, midpoint sum, or trapezoid sum. I feel like the flow of this lesson is easy, hard, easy. The easy part is, all right, yeah, we drew some rectangles. We add up the rectangles, we get an approximation. Maybe it's a good approximation, maybe not. Maybe it's close enough, maybe not. But I get some approximation for area. Got it. Add up the rectangles. The hard part is, whoa, all this weird symbol stuff. What does all of it mean? Well, all of it means is we're just going to add up the area of rectangles. So now we're going to go back to the easy part and just add rectangles. Number 1, let f of x be a continuous function. Selected values of f of x are given in the table above. So remember, f of x, that's the y values, that's the heights. I'll have to be careful about which height we use, but those are the set of heights. Okay. Part A, estimate the integral from 0 to 140 of f of x dx. Okay, well, let's remember that what that means is the area under f of x from 0 to 140. But now we have like a shorthand way of asking for that. Rather than typing all that out, find the area under the f of x from 0 to 140. We use this integral with 0 and 140, and we know that that means area. So area is equal to that integral. And I don't know enough to find the exact area, so we are going to approximate it with left rectangles. These sums are called a variety of different things, so I'm trying to use all the different words. A left sum, left rectangles, left Riemann sum. But the key word there is left, right? Because that tells you which height to use. Okay, so there is a rectangle from 0 to 20. On one side it has a height of 100, on another side it has a height of 90. I kind of like to visualize what's going on here. So what height should I use? I don't need any of this other information. From 0 to 20, if I want the left rectangle, which height should I use? 100. I should use the one on the left, right? So we said base times height. What's the base? I guess this is the tricky part. I don't care about any of the others yet. How wide is the base? I'm going from 0 to 20. 20. So 20 times 100. That's my first rectangle. All right, my next rectangle will go from 20 to 30. Let's start picking on people. So I need a base and a height. So Zach, maybe it'd help if I covered up everything else. So Zach, from 20 to 50 with heights of 90 and 80, what's the base? Which base? 30. Good. Good. He was not fooled. He didn't pick 20 or 50. That width is 30. So the base is 30. Avery, which height should we use?
90.
Why 90? Because it's on the left. Once you get the hang of these, and maybe you're already there, you're going to be like, that's it? Like I'm just doing base times height, plus base times height, plus base times height? Yep. All right, next one. Let's see how many colors I can get here. Let's go 50 to 70. So I need a base and a height. So Leah, from 50 to 70 with heights of 80 and 80, what's the base of that rectangle? 20. Good. That width is 20. Alec, what's my height? 80. How did you? They're both 80. The one on the left. The left 80. So 20 times 80. We'll speed up eventually on these, but no need to rush things yet. So the next one is from 70 to 100. So I need a base and a height for 70 to 100. So Sophia, what's the base? 30. And Braden, what height should I use? The 70 to 100.
90.
If I want a left-hand sum,
Oh, we're on left.
We're on the left hand, 80. So 30 times 80. And then lastly, I think I'm out of, oh no, one more. From 100 to 140. Marie, what's the base? 40. And Helen, what's the height we want to use? 90. And we love safe stops, so we're done, right? If the grader wants that number, he can grab a calculator and type it in. Now, we're going to do the right sum, we'll do the trapezoid sum, but let's pause for a second. This sometimes throws people off because they're like, wait a minute, I didn't use all the heights. Well, correct, you did not use all of those heights because there were 1, 2, 3, 4, 5 rectangles, 6 heights because you had a beginning and an ending height. We used all the left-hand heights, though. So just be careful. Some people, they start doing this too fast, and they try to use all the heights, and that's never the case. All right, using a right Riemann sum, I used up all my colors. So area by right rectangles. Right rectangles. Okay. Oh, I don't know if I use colors, I'm going to mess this up. So that first rectangle. Let's see if we can do it without colors. I bet we can. Laura, what's the width of the first rectangle? 20. Maddie, which height should I use?
90.
Why 90?
Because it's on the right.
Because it's on the right. So that first rectangle, so there's still a first rectangle, but it's 20 times 90. Will, on my second rectangle, 30 is the width. Evan, what's height should I use?
80.
80. Why 80? It's on the right. And then my next rectangle, Claire, what's the width of that next rectangle? We're on the third rectangle, from 50 to 70.
20.
So 20 and 80. So 20 times 80. And then 30 times 80. And then that last one. Hector, give me the width and the height of that last rectangle.
40 and 130.
40 and 130. Uh-oh, what'd that mess up? It should be 30 and 90. Good catch. On that rectangle, that width is 30 and the right-hand height is 90. Yes. Good catch. Laura?
So area, you put an estimate sign after that, and then the right rectangles you put an equal sign?
Yes, because my right rectangles, that's the area of my right rectangles,
Yeah.
but those are an estimate for the area.
So, and then in the one above, it should also be equals?
Well, the way I wrote this one, this is the exact area, and it is estimated by this. If I put it all in one line, I could have put an equal sign from here to here.
Okay.
Okay, trapezoids. 5 subintervals as designated in the table. So the area estimated by trapezoids. I'm trying to give myself more room because it takes more room to write out the area of a trapezoid formula. So it's the average, the base times the average height. The base times the average height. So what's the base of that first rectangle? Or not rectangle, trapezoid. What's the base of it? How wide is the base? 20. And then the average height, I'm just going to use both of them. I'm going to put them in order. Some people like put the smallest one in the biggest one. It doesn't matter, but to me it makes more sense if I put them in order.
So with the trapezoid and the midpoint, like, get you the same sum, so like the same areas?
If it was a linear thing, they would get you the same. But if it was like a parabola or something, they wouldn't necessarily get you the same. Because the midpoint is you pick the value at the midpoint. The trapezoid is you take the average value of the endpoints. So if it was a line in between there, then yes, those are the same thing. But if it's got some curve in there, then they're not the same. It's a good question. We're going to get to that in a minute. Some people will do the average in their head, like obviously the average of 190 is 95, and they'll just write 95. It would probably be better, not probably, it would be better if you would show what you're doing. You're more likely to get full credit by showing that you know it's the average of the heights, rather than you doing the average in your head. All right, the next one, the width is 30, and 90 plus 80 over 2. And then the next one is, this is just be careful as you count here. The width is 20. 80 plus 80 over 2. Obviously that's 80, but whatever. Width of 30. 80 plus 90 over 2. Width of 40. 90 plus 130 over 2. A lot of keeping up with things, but not a lot of difficult concepts here. Add up the rectangles. Either use the left height, the right height, or use a trapezoid. Okay, now we're going to get to some calculus here, rather than geometry. Given that the second derivative is greater than 0, Tristan, what does that mean? What's the second derivative tell us about the graph? It's concave up. Good. So this means that we are concave up. For the whole graph, or at least 0 to 140. Is the approximation in part C, so that's the trapezoids, an overestimate or an underestimate? Explain your reasoning. Okay, well there's like a large, every textbook has this big table of things that makes you feel like you can memorize it, but you don't memorize it. You sketch this, you sketch on some trapezoids, and then you figure out if the trapezoids are over or under your curve. So in order to see this, we want to draw exaggerated concave up, and we want to draw relatively few trapezoids, because we don't really want an accurate answer. We want to know how bad the answer is. So concave up. Again, I don't want to be barely concave up. I want to be like super concave up. And I don't know, let's put 3 trapezoids in there. I think that'll be enough for us to see. Actually, the fewer the better on seeing if it's over or under. So if I draw trapezoids, are my trapezoids over or under my curve? Over. So that's an overestimate. And your reasoning, this is where the reasoning is kind of nice. You can just say that trapezoids on a concave up will always be over. Trapezoids are always over or above or outside, however you want to phrase it, are always above a concave up curve. Probably means they're always under a concave down curve, but that's not, you don't ever memorize this. When you hit a question like this, you sketch it out and you figure it out. Because there's too many different combinations of, there are different rules for right hand, left hand, increasing, decreasing, concave up, concave down. It's too much to memorize. Just sketch it out. All right, let's try, oh, this one's a little bit different. What's different about number 2? Which sum are we using on number 2 here? Midpoint sum. Okay, estimate the area under the curve. We should remind ourselves what this means. This is area under h of t from 30 to 90. Area under the curve from 30 to 90. Okay, and it's got me a table going from 30 to 90. Using a midpoint sum with 3 subintervals. I feel like I got a lot of data there for 3 subintervals. So my subintervals, they'll need to look like this to get 3 of them in, rather than 1, 2, 3, 4, 5, 6 of them in. Okay, so the midpoint rectangles equals, let me get to everybody today. It's here anyway. Caden, what's the width of my first rectangle going to be? My first rectangle is 20. Good, because I'm going from 30 to 50. So that first rectangle has a width of 20. Graham, which height should I use?
You should use 7.
Why 7?
Because
It's the one in the middle. So 20 times 7. So 5 would be a left-hand sum, 10 would be a right-hand sum, 7 is the middle sum, the midpoint sum. All right, Lexi, on our middle rectangle there, how wide is that rectangle? Looking at that one is 20 wide. And Harper, which height should we use? Why 15? It's the one in the middle. And they told us to do a midpoint sum. So 20 times 15. And then my last rectangle. Emma, how wide is that rectangle? 20. And Audrey, what height should I use? And why 16? Because it's the one in the middle. So midpoint sum. People get thrown off by midpoint sum, I think, because there's like more data than you need there. So it feels like, wait, they give me all this information and I'm not using all of it. You're right, you're only using those midpoint heights. Sophia?
Doesn't midpoint, will it always give you like 7 or how many to use?
Yes, that's a good question. Because if it had asked for 6 subintervals, like here to here, here to here, we wouldn't be able to do it because we don't know what the midpoint is. So that kind of fits with your question of, they'll tell you how many to use, and it'll look like very few because they've got to give you the midpoint plus the other points. Question on that? Again, I hope you're thinking, what is this it? Like we're just doing width times height, width times height, width times height. That's it. Just be careful. Are you using the left height, the right height, or the middle height? But it'll tell you. And it's not like coded language or, we're not keeping it a secret. Use the midpoint. Number 3, use the left-hand side. Although number 3 looks different because they didn't give us a table. So approximate. We've written this out a couple times. Cody, what's it asking me to find here? The area below the curve. I won't repeat what the curve is. And then from what to what? From 0 to 2. So what it's asking me for is the area under that curve from 0 to 2. Using a left Riemann sum, 4 subintervals. Let's see. Some people would try to convert this into a table problem, and then it would look like all the others. That would be fine. Other people would try to draw the graph, but I don't really want to. I don't know I mean, I kind of know what a cubic looks like, but I don't know that cubic well enough to graph it. So I'm thinking sort of what the graph would look like. I know I'm going 0 to 2. I need 4 subintervals. So let's see. How much is each base going to be? Where did 1/2 come from? You're right.
Divide 2 by 4.
So it's b minus a over n. That sounds fancy. But let's make it less fancy. It's the total width divided by the number of subintervals. Most of you probably wouldn't even write all that stuff out. You'd be like, oh, it's 2 divided by 4 is 1/2. Every 1/2 is where my intervals will be drawn. Okay, so my area is going to be approximated by, let's see, how wide is my first interval going to be, or first subinterval, I guess I should say? How wide is my first rectangle going to be? 1/2. And which height should I use? I want to use the left-hand height, so that would be the height at 0. F of 0, remember that means y value at 0, that means height at 0. That'd be my first rectangle. I have no idea what that height is, so pictures definitely not to scale. Gone through everybody. What's the width of the second rectangle? 1/2. And which height will I use? The height at 1/2. Because I want the left-hand height. And then, who knows, maybe my third rectangle is even higher. Who knows? Maybe it's negative, but it doesn't really matter. Ryder, you just got back, but what's the width of that rectangle? From 1 to 3/2. How wide is that? That's 1/2. And if I want the left Riemann sum, then I want the height. Right, or which height do I want? Height at 1 or height at 3/2?
Height at 3/2.
If I want the one on the left.
Oh, 1.
Yep. The height at 1. And then my last rectangle, another width of 1/2, and the height at 3/2. This is not a safe stop, right? You can't safe stop with function notation. You have to do the substitution. So if somewhere I would explain what f of 0 and f of 1/2 and f of 1 and f of 3/2 are, then I could safe stop that. And a few of you have started doing that on the test. Like, you'll leave that and then tell me what each of those are. That is okay if you do that.
For questions like this where it says equal subintervals, could we say like the area of f of 0 plus f of 1/2 plus f of 1 plus f of 3/2 over 2?
Yep. So if you have equal subareas, what he's saying is, like, all of my bases are 1/2. So why don't I just factor the 1/2 out front? And you can. Once you kind of get used to these, you can do that. I'm hesitant to do that because then people do that every time. But when that only works, when, fill in the blank, when is the only time you can factor out that base? If the bases are equal. So be careful. Some of you will kind of adopt that and factor it out. Others of you are like, nope, just going to do base times height plus base times height plus base times height every time. And there's nothing wrong with that. Okay, now I got to figure out what all these things are. Yeah, let's do it that way. Rather than rewrite all of this, if I just say what f of 0 is, then f of 0 is defined and it will count as a safe stop. So if I plug in 0, that would be negative 0 cubed plus 2 times 0 squared plus 1. That's equal to 1, of course, but I can safe stop. Like you sort of have this nested safe stop thing going, and it's completely okay. As long as everything is defined, you're all right. F of 1/2. I look at my function, I plug in 1/2. So negative 1/2 cubed plus 2 times 4th plus 1. Don't even care what it is. I've told the grader what it is. He can plug it in. Like it's calculator ready. F of 1, negative 1 plus 2 plus 1. And I'm doing a little bit of math in my head, but when it gets to 3/2, I don't want to do that math in my head. So I'll just leave 3/2. I mean, squaring 3/2 wouldn't be bad, but why risk it? Just leave it alone. And the combination of all of that is a safe stop. Just be careful, you've got to include the f equals things. You can't just leave it as f of 0, f of 1/2. You've got to explain what those are. If you explain what they are, then you can leave it alone. Okay, so that one was a little bit different. It was a little bit trickier because rather than just like looking at a table and grabbing the left-hand height, we kind of had to draw our own table or think about things to think where the left was or the right was. Number 4, and final. The amount of water in a draining tank is given by a strictly decreasing function. Strictly decreasing means that it never levels off. It's always decreasing. All right, we're back to a table, so that's nice. Use a right Riemann sum with 4 subintervals to approximate the area under that curve. So instead of me doing this one, why don't you do this one? And again, you don't need a calculator because you're not going to actually do all the numbers. Just set up the... Is your answer to part A an overestimate or an underestimate of the actual value of that area? Okay, well, what do we know about... So I want to sketch something out. What do I know about W of t that would help me sketch it? Strictly decreasing. So I don't know if it's concave up or concave down. It doesn't tell me, so it must not matter. So it's decreasing. And I want to find, or I'm using, let's see, right hand. This was a right Riemann sum. So if I'm coming from the right on each, for each rectangle, what do you think about my approximation? It's definitely under. All those rectangles are under. And again, the reasoning on this, you can kind of just restate the problem because right rectangles for a decreasing function are always under. Again, that reasoning stuff, you don't memorize that. Like you could come up with a table because that means the right rectangles on an increasing function would be an over, or the left rectangles on a decreasing would be a over, and the left on increasing would be under. But like, don't. Like, just draw the picture when it comes to that stuff. All right, the next worksheet in the packet is, again, it should feel like almost a day off. Like, what? We're just adding up rectangles? Like, yep. So it's misnumbered. I don't know what happened. That shouldn't be worksheet 2. That should be like worksheet 4. And it gives you a bunch. What I would definitely try some of is when you get to number 10, it's all those over versus under. And so there'll be a lot of little pictures on number 10. Yeah. In fact, let's look at number 10. I'm not worried about the others. The others are, you know, the area of a rectangle. So let's flip to number 10. And why don't we try... So we get some of these kind of already. Well, let's just try A and B. Just try A and B.